Single wire earth return transmission line. This is the most simple of transmission lines types. There is only one conductor carrying AC current, and the return current flows in the earth. Our task is to calculate current distribution in the earth and the voltage drop in the conductor. And also we will calculate the inductance of the transmission line. The line parameters are the following. The current is 10 amperes, root mean square value. AC frequency is 50 Hz. Line length is 10 kilometers. Soil conductivity is 1 millisiemens per meter, and the rock band conductivity is 0.1 millisiemens per meter. The conductor is made of aluminum. The soil thickness is 10 meters and the rock thickness is 140 meters. Okay, let's start QuickField now. In QuickField I create new problem. The problem name is SWER. Next. Problem type is AC magnetics. Frequency is 50 Hz. Model class is plane parallel. Length units are meters. Line length is 10 kilometers. Also I will include the electric circuit in the analysis, so I type in the file name here. Circuit. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I will draw it here. To draw the model I switch to the insert mode, insert shape, circle, and the conductor diameter is 5 millimeters. The conductor is placed 5 meters above the ground surface, so I 5 meters here. Insert. Close. Zoom to fit. Here is the conductor. 5 meters above the ground surface. Next I will insert the soil. It will be the rectangle. Soil layer thickness is 10 meters and the width will be 100 meters. Insert. Now let's take a look. This is the soil layer. Next I will draw the rock bed. It is located just beneath the soil, 10 meters down. The rock bed thickness is 140 meters and the width the same, 100 meters. Insert. Okay, zoom to fit. Now I should draw the air. Switch to the insert mode, select the line type to be the half arc, click and drag to draw the arc. This would be the air. The geometry model is ready. Now we should assign labels. Through labels we will specify material properties. Switch to select objects mode, click the object to select and type in the label name. I have selected the block and the label for this block is the rock. Here you can see the label appeared in the tree, and now if I click the label, the body will be selected in the geometry model. Now this is the soil, this is the air, and I will select the conductor. Magnetic field is distributed in infinite space, but the magnetic field fades rapidly, so we may consider that at some distance away from our transmission line the magnetic field is 0. So For this boundary, I will assign label 0. Now let's specify physical properties. Double-click the label name in the tree, and for the air I specify magnetic permeability, which is 1. OK. For the rock I specify magnetic permeability, which is 1, and the electric conductivity, which is 0.1 millisiemens per meter. OK. For the soil I specify magnetic permeability, which is 1, and electric conductivity, which is 1 millisiemens per meter. For the conductor I specify magnetic permeability of 1, conductor is made of aluminum, electrical conductivity 37 megasiemens per meter, and we should also specify the current. But we have electric circuit in our simulation project, so all sources must be specified in the electric circuit. OK, so I open the circuit file. OK, and here I drag all conductors. Conductor, rock, soil, and I add the current source. The current source value is 10 amperes, which is root mean square value. In QuickField you should specify the magnitude, so I type in here 10 times square root of 2. OK. Now I connect the source and the conductor with the wire, and the returning current flows back to the current source through the rock and through the soil here. That's all for the electric circuit. Switch back to the geometry model. Here we should assign label to the edge 0. As I said, we believe that far away from the transmission line conductor, magnetic field fades to 0. So I specify 0 magnetic potential at this boundary. OK. Model and data are ready, and before I start the analysis I should build the finite element mesh. Just click this button and the mesh will be constructed. Now save all problem files and run the analysis. The problem has been solved and we can take a look at the results. Here you can see the magnetic field lines and the electric current density color map. You can adjust the picture and switch, for example, the color map of the flux density. You can zoom in. The magnetic field picture doesn't look nice. In real case, the magnetic field lines must be smooth curves. We might need to refine the initial coarse mesh to get more accurate results. Solve and refine. OK. Now let's again take a look at the results. Much better, but still we have these sharp corners. So let's run solve and refine again, and let's specify at least 5 iterations to refine the mesh, and 0 since we have professional version with unlimited mesh size. OK. Now let's take a look at the results. Let's zoom in. Now the field picture looks physically correct. OK. To get exact field parameters, you can use the local values picker. Just click any point and you will get the current density, the magnetic flux density, and other parameters. You can use contour tool to make XY plot. For example, I will draw the contour from the conductor to the Earth surface, click XY plot, and here on the plot I will take a look at the magnetic field strength. This distribution. And the exact values you can see in the table. Coordinates, flux density, field strength, and other parameters. And you can use contours to calculate integral values. For this contour I can calculate the integral magnetic flux, and if I divide the flux by the current value I will get the inductance. You can also select the entire blocks. Contour clear. Let's zoom in. Click inside conductor, and for the conductor I can calculate the total current, I can calculate the joule heat per 10 kilometers of transmission line length, and other integrals. And remember, we have an electric circuit in our model, so we can see the results in the electric circuit too. Click any element, and for this element you can see the current and the voltage drop, again per 10 kilometers of transmission line length. And if I divide the voltage drop by the current value, I will get the transmission line impedance per 10 kilometers. If you search for the single wire earth return on our website, you will find the example page. Here you can read about problem setup, take a look at the resulting pictures, and you can download the simulation files here. Simulation files may be opened and viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.